All right, the topic for today is to delve into the concept of inductors, more so than we have in the past. And inductors are passive devices. Inductors are called coils. If you look at this guy, it really does look like a coil of wires that has been wound around a donut-shaped form. There's another one here. You can see the windings also around a donut-shaped form. This one is covered by a wrap, but inside of the wrap happens to be many wires wound around cylindrically. And there was one more. Haha, here we go. This goes to show the typical inductor that is wound around a ferrite core. Ferrite is iron dust compound. Let me just go ahead and focus this down here so you can see this a little better. Yeah, and that all of these are inductors and bear the characteristics of induction. Here is a transformer. This is actually an inductor, not a transformer. Let me show you this in a moment. So fundamentally, inductors can be nothing more than a coil of wires of a very specific diameter, of a very specific length, be from end to end, and also specific distance between the wiring. Now, we're able to enjoy the property of induction by shooting a current through this wire. By running a current through this wire, you've seen me demonstrate in the classroom with a piece of transformer wire. When I shot electricity from a 9-volt battery into that wire and held a magnet to the wire was either repulsed or attracted to the magnet, depending upon which way we polarized the battery source. So if I polarized the battery source one way, and I held the magnet up to it, the wire would have been repulsed or attracted, depending upon the polarity of the battery. So what causes that? What causes that is this: when we run electricity through any piece of wire, separate of being a coil, let's just say we have a piece of wire, and by running electricity through this piece of wire, if I run DC through this in one direction, electrons flow in one direction, there will be a very specific magnetic field that is developed around this wire. And that magnetic field can interact with other wires, other magnetic fields, or fixed magnets and cause a reaction. So by coiling the wires in this fashion, we're concentrating the magnetic field effect between each of the windings. So each winding has its own magnetic field and will interact with the magnetic field of the one next to it, to the one next to it, to the one next to it, to the one next to it. And it creates a very interesting phenomenon where these devices are very useful to us in electronics. Now, what is their behavior in comparison to capacitors? You've seen me demonstrate with a capacitor. We hook up electricity to a capacitor and we remove the source of electricity. That capacitor can hold a charge, yes? And you've also seen me demonstrate that the capacitor can discharge very quickly and cause a spark. And that was rather dramatic, that time that we were able to damage the shaft of a shiny steel screwdriver shaft by the arcing of a large capacitor. Well, inductors behave similarly in this fashion. They don't store a charge. What they do is they build up a magnetic field. And as they build up a magnetic field, as soon as we release that battery source, then the magnetic field collapses, and it can collapse very quickly. And in that collapse of the magnetic field, it can generate a voltage. So it takes voltage to build up the magnetic field. And once we remove the voltage source, then the magnetic field dissipates. The terminology that's used is that it collapses, and when it collapses, we're able to determine a voltage between the terminals. Now, we've also seen this. Another characteristic of the coils is this. They are, and since they're nothing but wires, nothing but coils of wire, there is a DC resistance. So if I go to take a digital multimeter and I set this up in the ohm meter mode, do that, and I go to connect to, let's say, this particular device here, go to measure here, and go to measure the other one here. What do you think we're going to measure if this has a lot of inductance, if this has lots of Henrys, however it's constructed? Let me unravel this spaghetti here, try to neaten this up a little bit. Okay. And so what do you think? If this has a lot of inductance, if this has a lot of Henrys of inductance, do you think that would equate to be a lot of ohms, yes or no? Is there a relationship between lots of Henrys and lots of ohms? There is slight relationship. Lots of Henrys doesn't necessarily give us lots of ohms. Lots of Henrys occurs because we're using lots of wire. But when we go to measure the wire, the resistance of this lead here through the coil all the way to the end where it comes out on this side, take a look at how many ohms this works out to be. It's a fraction of an ohm, if even that. Yeah, look at that, 0.3 ohms. So we're basically measuring the resistance of wire. So the property of inductance really happens and is significant to us once we run electricity through it. But passively, if we were to just measure the ohms of this particular guy, it's less than an ohm, okay? So let's go ahead and try this with another inductor. Let's go ahead and try it with this particular guy. Very small, and wow, it doesn't even, it barely shows up as a 0.1 ohm for this particular one. And if I go to measure another one of these using DC, right here, 0.8, the LCR meter, yeah, one of those. I'm going to measure the inductance, thank you. And here's the bigger coil, and we go like so. Measure this guy, might have a few more ohms, possibly. There's a lot of wire there. Yeah, it's still 0.1, 0.2 ohms, not a whole lot of ohms. Now, if I go to measure a larger inductor, and this is a larger inductor, this has 2 wires. This has got a massive amount of coils of wire around here, and it's also has an iron core on the inside. It's got an H-shaped iron core in there, and so the iron is there to help focus the energy of the magnetic field. But let's measure the ohms of this guy and just see where this guy sits, because this is a ginormous inductor. Wow, a whole 49 ohms. And considering all of our labs have been 100 ohms, 200 ohms, 1K ohm, 10K ohm, thousands of ohms, the amount of ohms here is really inconsequential. So the characteristic we're concerned about is not the DC resistance of the component, but how it behaves when we run electricity through it. Now, there is a way of testing these inductors, and we will be testing these inductors not with a digital multimeter for reading ohms. We can do that to see if there might be a break in the wire. Sometimes that does happen when you're working with a inductor. If the thing just does not behave the way it should, then one of the reasons that can be is that one of the wires deep inside may have a fracture. And if there's a fracture, then this will not work properly. We'll use this device here. This is our LCR device. Turn this on, and we can use this to test inductors and capacitors and resistors. But let's go ahead and hook this guy up and see what it reads in terms of inductance. Okay, let's go test. Analyzing, 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 analyzing. Okay, so it does read, if you can see that. Let me go ahead and bring this down so you can see a little more clearly. Focus. All right, it's giving us an inductance reading, and it shows us 905.0 microhenries. So that is a characteristic that this little device can test what the inductive behavior of this coil is. The digital multimeter only shows us DC resistance of the wire. So you see how these two instruments are different. The digital multimeter does what? It measures only the DC resistance of the wire, whereas an inductance meter will actually measure the inductance of these coils in terms of their value in henries, millihenries, or microhenries. Let's check this particular guy here and see where this one stands. So we had 900 microhenries there. This one hit test, and let's see where this comes in at. This guy comes in at, okay, 312 microhenries. And the littlest one that we have here is probably this guy here. It's the least amount of windings, does have a ferrite core, so there may be some hope for some value of significance, but I suspect this one will be very small. Hit test, analyzing, and let's see how this checks out. It's so low it can't read it. I'm going to need something more sensitive than this particular instrument. Let's go ahead and measure this big inductor. And this big inductor, go hook up here and hook up here. This one should be pretty significant. Yeah, it's more than millihenries, isn't it? It's a whole 1.02 henries. So that is equivalent to 1,020 millihenries, or 1,020,000 microhenries. It's huge. All right. Now you may have seen off to the side here. Now that's an inductor. It has two leads. This has two leads. And off to the side here, you may have noticed I had something some of you might recognize. This is a transformer. A transformer is a huge inductor that has two sets of windings that are placed in opposition to each other, very close opposition to each other. And what it's used for is there is a transformer. There's a transformer in all pieces of electronics equipment that you have that plugs into the wall. So where do transformers come in is here. This is the cord that plugs into the wall, and typically what you have hooked up to the cord, it could be a microwave, it could be your television set, it could be your computer. Whatever it is that you have that plugs into the wall will send that AC through a pair of wires that goes into what we call the primary side of a transformer. I'll talk about a transformer in greater detail in a few minutes. But it goes into what we call the primary side of the transformer. Let me flip this around because this will be the typical orientation which we discuss transformers. So we have the primary wires coming in on the left-hand side of this transformer. And guess what we call these wires that come out on the right-hand side? If these are called primary, then this side here is called secondary. So we have secondary wires. Now, more often than not, transformers that you are likely to encounter in your home, connected to your computers, connected to your television sets, connected to your gaming devices, even your cell phone chargers have little transformers. The idea behind most of the transformers we use is that it will step down voltage from 120 volts to something less, maybe 20, maybe 30, maybe 40 volts, but something less. So the terminology, when we bring the voltage from a higher level to a lower level, this is called a voltage step down transformer. We do have voltage step up transformers. Where those occur is if you have a friend visiting from a foreign country, and let's say they need to plug their computer into a wall outlet for charging their cell phone or charging their computer, But lo and behold, where they came from, the voltage was 220 to 240 volts, whereas we're only 120. So we're going to need something in order to allow them to plug in their devices to work. So we would put 120 volts on this side, and with a different transformer, we would have 240 volts on this side. So the primary would come in at 120 volts, and the secondary would come out at 240. Isn't that higher? We go from low 120 to a higher 240. That would be called a voltage step-up transformer. So we have transformers that work a couple of different ways, and these are really remarkable devices, and we'll talk more about these later on this afternoon. And we talked about this before. Inductance, the symbol is L. The devices are known as chokes, coils, also known as inductors. Those are the names that are given to the devices. So if the property was resistance, the symbol would be R, and the devices would be a resistor. But here, the concept is inductance, the symbol is L, and the devices are chokes, coils, and inductors. What are the schematic symbols? The schematic symbols come in two flavors. One type of flavor will look like that. Another one could also be drawn and actually look like coils, like that. So those are the two different ways inductors are shown in a schematic format. Now, the property of inductance, the units, units are measured in something called henries. Henries. And the symbol for henries is equal to a capital H. Capital H. Now, and the characteristic of inductance is ability to create and store a magnetic field when energized with electricity. That's the property of inductance. So this little guy right here and this little guy right here, when we go to hook them up to a 9-volt battery, there will be a magnetic field that will be built up. As soon as we remove that magnetic field, guess what? As soon as we remove the voltage source, the 9-volt battery, whatever we hook up, the magnetic field will start to collapse. When it starts to collapse, it will push current out of that device, even though there's nothing hooked up to it. So that raises a very interesting question. When we go to hook an inductor up to a voltage source, take a look at this. I'll draw a schematic here, and set a switch and put a inductor in here, and let's give us a resistor, like so. So we have an R, we have an L, and we have an SW, and you have a VS. Looks a lot like our capacitor charging circuit, doesn't it? Guess what you're going to observe when the switch closes. When the switch closes, this will behave with our friend, the time constants that we've discussed before. So on this axis, we have time, and time will be measured in units of tau. So 0 tau, 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. And then we would simply have some maximum that occurs. All right. Now, the moment we close the switch, what's likely to happen? Well, if you remember, the capacitor voltage took a while to charge up to maximum. If it was a capacitor that we discussed a couple weeks ago, the moment we close the switch, the voltage on the capacitor starts off as nothing, but after 5 time constants, the voltage on the capacitor goes all the way up. And we had a very useful mnemonic called Eli, the Iceman, that helped us remember that relationship, which one came to maximum first. Previously with capacitors, current was at maximum, then voltage happened to be maximum after 5 time constants. But here we're talking about a coil, so we're not going to use Eli. And Eli tells us which comes first. The E comes before the I, because if you recall what we said, that E is the other symbol for voltage. And so for inductors, voltage will be maximum first. So what happens is the moment we close the switch, the voltage across this guy becomes at maximum. All the voltage will be, so if I give you a number, let's say this were 5 volts. At the initial moment when the switch closes, if I put a voltmeter right here and measured this, at the moment the switch closes, all of the 5 volts will be across the coil at the moment the switch closes. No current flows yet. So if there's 5 volts here and 5 volts here, is there any voltage left to go across the resistor? None. Now think about this, Ohm's law now. Think about Ohm's law. You have V, I, R. If the voltage across the resistor is none, because all 5 volts is across here at the moment the switch closes, if this is a 0, how much current are you going to calculate? You have a 0 divided by ohms. What are you going to calculate? 0 current at that moment. So current will be down here. And this will be IL equals 0 amps. Whereas up here, your VL is equal to maximum at the very beginning. Now, what happens in the first time constant, when we were talking about capacitors, the capacitor voltage charged up 63.2%. In the case of a coil, the coil will drop its voltage by 63.2%. It'll come down. And the current, conversely, will go up 63.2%. Because as the voltage drops across this guy, you will have some voltage here. Let's go ahead and do some quick math on your calculators and see what our voltages will be after 1 time constant, okay? This is very easy to do. We have a 5 volt source, yes? And 5 volts is what we're starting with here. So 63.2% is equal to your change. 100% minus this, 100% minus this gives you 36.8%. Is that correct? So that means that this voltage, your V equals your VL drop per tau. Each tau, the voltage will drop to that amount. It'll drop by 63.2%. It'll drop to the amount of 36.8. So watch this. 5 times 0.368. It will drop down from 5 volts down to, what do we have here? 1.84 volts. 1.84 volts. And then within the next time constant, it'll drop down another 63.2% of that amount. But what will it drop down to? We will multiply by this decimal. So times 0.368. Oops, I did a divide. Silly me. Let's go ahead, clear. So we take the 5 and times 0.638 equals the 1.84 times 0.368, and it drops down to less than a volt. It'll drop down to here, where this is now 677.12 millivolts. And then times 0.638 again, and it'll drop down to here, 249.18 millivolts. You kind of see what's going on. It will follow this curve like so, coming down. After 5 time constants, your VL is approximately 0 volts. What happens to IL? IL increases by 63.2%. So it will come up to 5 times 0.632. It will come up to 3.16 volts in that first time constant. And then it'll go another 63.2% and more and more and more. And its curve comes up this way. So after 5 time constants, your IL is equal to maximum. So this is the reverse behavior of a resistor cap combination, as evidenced by our memory tool, Eli the Iceman. So remember, in Eli the Iceman as a memory tool, the C stands for capacitor, the L stands for inductance. And when you have an inductor circuit, as we do here, which property occurs before the other? Voltage will occur before current, and isn't voltage at maximum before current of the coil reaches maximum. There is a phase difference between these two quantities, okay? Okay, so a couple of things. When I go to discharge this thing, let's go ahead and analyze what happens when we discharge this thing. Let's keep this guy handy. Inductors in series. So this was L1, L2, L3, and this was 10 microhenries, 30 microhenries, and 15 microhenries. Then LT is equal to L1 plus L2 plus L3. It follows resistances and behavior. So when you go to do this, 40 plus 15 is 55 microhenries, okay? And the same behavior occurs when they are in parallel. So when you have them in parallel, like so, and like so, if I had an L1, L2, L3, and I said that this was 50 microhenries, 25 microhenries, and 50 microhenries, you might have figured out that LT should be somewhere around 12.5 microhenries. And you'll say, wait a minute, how did that happen so fast? How do we do that without a calculator? The same way we would do this if these were resistors. Do I have a pair of devices that are in parallel? Are they of the same value? Remember what we did when they were resistors. If I have a pair in parallel and they are of the same value, I can combine them into a singular equivalent. So this would look like this. I would still have an L2 at 25 microhenries. Sorry, I'll bring this up so you can see this a little better. So 25 microhenries. And then over here, I would have a coil. This would be LEQ1, and this is equal to L1 parallel with L3. And this would work out to be 25 microhenries. A pair of those, take that number, divide by the number that, take that value and divide by the number of devices that share that value, which is 2. 50 microhenries divided by 2 is 25 microhenries. So now we've taken 3 coils and reduced it down to 2 coils. And because these two coincidentally happen to have the same value, guess what? They give you a single total of 12.5 microhenries. So the nice thing about coils in series and coils in parallel is they follow the same rules as resistors. So your calculation and analysis of their circuit behaviors in this regard should be pretty straightforward, okay? Any questions so far? All right. Now, if we go back to the time constant for a moment, let's come back to the time constant for a moment. Tau, we said, that symbol is TAU, and TAU time constant. And in the case of a resistor was R times C. In the case of a coil, it's L over R. So if I happen to have a 550 ohm resistor, and I happen to have an L, and I don't remember what this one was, but we can measure it real quick. And let's go ahead and use this L value. So go ahead and hook up to there. And let's go ahead and hook up to here and do the analysis. We're going to use this number in a second. And it says the winner is 902.8 microhenries, 902.8. All right. So this would be 902.8 microhenries over our 550 ohms, 550. Go ahead and do that calculation and tell me what one-time constant calculates to be. And I'm going to be calling on a classmate here in a moment for that calculation. So clear. So we punch in 902.8. How do I key in micro? That would be exponent, change sign. Micro is change sign what? 6. And then divide by the 550 ohms. And before I hit equal, Isaac, do you have a calculation for us, please?
1.64 micro tau.
Time is measured in units of seconds.
E.
Seconds.
Seconds.
Yeah, 1.64 microseconds. So that is equal to 1 tau. Okay, 1 tau is 1.64 microseconds. So how long would it take for this coil to reach full charge of its magnetic field? That question goes to ESYS. How would we determine the full time for this to reach the full magnetic field?
Multiply by 5.
And multiply by 5, and what do you get?
I got 8.21 microseconds.
And we would look at my calculator and concur. Yes, that would work out to be 8.21 microseconds. So 8.21 microseconds. So now we figured out the time for 1 tau and the time for building up to a full magnetic field. Okay, good job there. All right. Now, practical applications are several. One that's discussed in your homework, and you have to do a little bit of research about this, but let me help you out with this. And that has to do with your anything that has a coil at all. It has to do with transformers. Actually, let's talk about transformers. Then you can understand the coil of your car a lot better. So transformers. And transformers are drawn this way. You have one set of coils like so. You have a pair of parallel lines, and you have another set of coils like so. You have several characteristics. This side of the coil is called primary. This side of the coil is called secondary. And the pair of parallel lines in here indicates that we have an iron core. And, my friends, that's what this device is. This big hunking thing that we have is a transformer. We have primary wires on one side, that we hook up our AC to, and then we have secondary wires on another side that we hook up our equipment to. So this is the physical transformer. Let's just move it aside. It's kind of big, clunky, and heavy. And let's talk about analyzing what goes on here. So there's several characteristics about this that are useful for you to know. We have something here called N1. We have something on this side called N2. We have something on this side called V1, something on this side called V2. And then there's going to be a current on this side, I1, and there's going to be a current on this side, I2. So first of all, N stands for number of turns. Can you relate to number of turns by looking at this coil? Are there turns around this donut? Yes. And is there some finite number of turns? If we go to count these all the way around, there's some finite number of turns. So in a transformer, we happen to have them packed where you can't quite see them all, because they're all sealed behind plastic and other things, but there are a finite number of turns in the, what do we call this side? Primary of the transformer, and there's also a number of turns in the secondary. So N stands for number of turns. So V1, I1, N1 all pertain to turns, voltages, and currents in what part of the transformer? In the primary. I2, V2, and N2 pertain to number of turns, voltages, and currents that occur in what part of the transformer? Secondary. Now here's the basic transformer formulas that'll help you with your homework. V1 over V2 is equal to N1 over N2 is equal to I2 over I1. Those are the basic transformer formulas. It's very easy to work your way around the math. It's not challenging, I hope. Then there's also F1, F stands for frequency, equals F2, and P stands for power, P1 equals P2. There you go. Those are the only formulas that you have to be concerned about with respect to transformers, okay? Now, where does this become interesting for us is if I go to put in some values. So let me go ahead, change the paper, and let's go ahead and put in some things in here. So I'm going to draw a transformer, iron core, and let's say I happen to have a 16:3 would be my numbers there, and let's say my V1 is 120 V. I am looking for V2 equals question mark. So as you go to look at this exercise, notice that I've written a number with a separated with a colon, 16 on this side, 3 on this side. What do you think the 16 to 3 represents? The 16 to 3 represents my N1 to N2. And so there's a very unique name to this. Your N1 colon N2 has a name. It's called your turns ratio. Sometimes it's written this way, N1 over N2, also known as your turns ratio. And the ratio tells us the number of coils in one side relative to the number of coils on the other side. So this is called what ratio? Turns ratio. Now, if I bring this back to this sheet that I've just drawn, I have a turns ratio that says 16 to 3. Now, don't let this mislead you. This doesn't mean we only have 16 windings, 16 coils in the primary and only 3 windings in the secondary. This would not suffice. There are many hundreds, if not thousands of windings in something this size, okay? And so all this represents is there are, for every 3 coils on the secondary, there are 16 coils on the primary. So this could very well represent 16,000 to 3,000 turns, okay? Now, how do we determine the V2? I will show you how. We were shown a formula, V1 over V2 equals N1 over N2 equals I2 over I1. Now, the pieces we need happen to be in this part of our formula. So if we recognize we're given an N1, already given an N2, already given a V1, could we find a V2? Let's go ahead and fill in the numbers. If we go to fill in the numbers, we would have 120V over V2 equals 16 over 3. Well, guess what, my friends? You got a pair of fractions with one unknown. You know how to solve this. How do we solve a pair of fractions with one unknown? We do a simple exercise known as cross multiplication. I'm running out of space. Cross multiplication. And so the result of cross multiplication would give us 120 times 3 is equal to 16 times V2. The 3 times the 120 goes on one side of the equal sign, and then the 16 times V2 goes to the other side of the equal sign. So that's how you use the formula, plug in the numbers, set up your math, now do the math. So what is 120 times 3? Isn't this going to be, okay, 360 equals 16 times V2. And how do I find 16? How do I find the V2? Is divide both sides by 16, yes? So when I divide both sides by 16, won't the 16 in the numerator and 16 in the denominator cancel? So that leaves me with V2. So all you need to do, 60, thank you. All you need to do is simply turn on your calculator and take 360 and divide by 16. Wei Ji, do you have a number for us?
22.5.
So it works out to be engineering, yes, 22.5 volts, yes? You have to call out volts. 22.5 volts. Well, guess what? We just calculated 22.5 volts. So we have big volts here, small volts here. Does that match this, the higher number of turns here to the lower number of turns? You betcha. Could we check this? Well, guess what? Let's go ahead and take V1 over V2. Let's take 120 and divide by 22.5. Let's go ahead and do that ratio right now. 120 and divide by our newly found 22.5. And Jackie, what do you have?
5.33.
Okay, so if we brought this all the way down to a singular value in decimal, it works out to be 5.33333333. Okay, we would call it, write it down as on paper as 5.3. So our turns ratio, we're going to check in just a moment. Let's go ahead and take 16 divided by 3, everybody. So 16 divided by 3 and hit equals. Lo and behold, it gives you the same number. Isn't that interesting? So our turns ratio is 5.33. And as long as we have a larger number in the primary and a smaller number in the secondary, then we say this. This transformer is a voltage step down transformer. Comma, and a current step up transformer. And I'm going to abbreviate transformer. Watch this carefully. And from this point forward, I will be abbreviating TRANS. In our world of electronics, can be reduced to a single letter X. So transformer can be reduced in spelling simply to X-former. And that's a very common nomenclature in our world of electronics. When people write down X-former, they are talking about a transformer. Okay, all right. So guess what? I gave you some new labels here. We said that this was a voltage step which way? Down transformer, and a current step up transformer. Interesting. we hadn't done anything with respect to current yet. We just only determined the secondary voltage. So I think this bears another practice exercise. Let's do another one. Okay, practice is always good. So here is another transformer. And I'm going to say this is 75 volts over here, and this is 18. And on this side, we will have 2.7. I am looking for V2 equals question mark, but I am also going to hook up here a resistor. And let's say R, and R is going to be equal to 220 ohms. So I am looking for a V2, and I am looking for an I2. So where do we begin to find the V2? What is the process? Yusuf, you lead us off here. How do I find V2? What tools do I have that I can use?
I mean, we're going to plug stuff into our turns ratio, right?
Okay, let's bring up our turns ratio and let's bring up that formula. So the formula, if you recall, was V1 over V2 equals what?
Equals N1 over N2.
Okay, so let's start there. That's a good starting point. And once we have the starting point, let's go ahead and plug in some numbers. And so our V1 was equal to 75, V2 we don't know, and then our N1 was given as 18, and our N2 was given as 2.7. We're looking for V2, so we're going to use this part of the transformer formula, turns ratio, voltage ratio, plug in the numbers, and the math here with two fractions and one unknown is what? We're going to cross multiply, and let's go ahead and write this out. 2.7 times 75 is going to be equal to 18 times V2. And V2 will be equal to, let's do our 2.7 and times 75. Isaac, what do you have? 2.7 times 75. What do you have for this first part?
I got 202.5.
Excellent. So we will have on this side 202.5, and that's equal to 18 times V2. Then we're going to divide both sides by 18. And when we divide both sides by 18, that will leave us only with V2, and V2 calculates to be what, Jacqueline?
$11.25 volts.
Okay, excellent. Hopefully we all agree that we should have 11.25 volts. So far, so good. Now we have just determined our V secondary, and we measure our V secondary between here and here. V2 is measured between this wire and this wire of our transformer secondary, and we discovered that V2 is equal to 11.25 volts. Well, we have a 220 ohm resistor. Do we have enough information to calculate our current? And so the current, Weiji, how would we go about calculating current?
We use the voltage divided by resistor.
Okay, which voltage?
V2
We use V2 over R, yeah?
R.
So 11.25 V over 220 ohms. And this calculates to be what value, Weiji?
51.14 milliamps.
51.14 milliamps. 51.14 milliamps. Is everybody okay with that value for I2?
Yes.
Okay, so far seems to follow along with Ohm's law and this part of our turns ratio, yeah? All right, so the next question becomes this. What is the value of I1? How do I find I1? There's no resistor on this side. You can't do Ohm's law. What do we do here? Think,
Because I2 divided by I1 equals to V1 divided by V2.
Okay, check this out. If I go back to one of my earlier sheets, remember I showed you the transformer formula as having three ratios equal to each other. Try to use the numbers that are given rather than numbers that are calculated. So in other words, try to use, in this particular case, these two fractions here, because you're given an N1, N2, and use that to calculate the I1, I2. The voltages, one's given and one's calculated. So try to always start with your givens. So if we're going to use this part of the formula, watch how we apply that here. N1 over N2 is equal to I2 over I1. If I go to fill in the blanks, I know that N1 was given as 18, N2 was given as 2.7, I2 we just calculated as 51.14 milliamps, and I1 we're looking for. So what you got to remember in this set of ratios, V1 over V2 and 1 over N2, but how is current stacked? I2 over I1. It's not I1 over I2, it's I2 over I1. So you got to remember we have this relationship for current to the other ratios. So as long as you remember that and write out our formula correctly here, I2 over I1, put in the numbers, let's go ahead and do a cross multiplication here to here, and we will have, in this particular case, 2.7 times 51.14 milliamps, and that's going to be equal to 18 times I1. So let's go ahead and do that. What is 2.7 times the 51.14 milliamps? So I'm going to times 2.7 since it's still in my calculator and hit equals. Yusuf, you have a number for us for this part of our equation?
138.08 milliamps.
138.0. I'm using all my memories instead of retyping it in, so it's okay. Milli, and then that will be divided by 18 in order to calculate my I1, yes? Because I'm going to divide both sides by 18. So divide that by 18. Now what do you get, Yusuf?
7.67 milliwatts.
Current.
Current
Yes,
amps.
milliamps.
What am I writing here?
7.67 milliamps, okay? So have we just determined the primary current? Now, let's do some double checking to make sure everything is on track. So you now have an I1, you had an I2, you have all the rest of this. Let's just double check. V1 over V2, that's 75 volts over 11.25 volts. Let's do that ratio to a single value. Instead of writing it as a ratio, what does that calculate to a singular value? 75 divided by 11.25. And Weiji, what do you have?
6.66.
Works out to be 6.67, okay? Okay, that's equal to the ratio. Now, suppose I take N1 over N2. N1 was 18 divided by 2.7. So Yusuf, can you give us this calculation? The 18 divided by 2.7, what's that work out to be?
You already have it on the screen. 6.67.
How about that? 6.67, same ratio. Okay, well, let's do one more check. The last check in our third ratio was I2 over I1, and I2 calculated to be 51.14 milliamps, and I1 was 7.67 milliamps. We'll skip the millis because they're both millis. the numerator and denominator, so you don't even have to key those in. Let's just go ahead and punch in the whole numbers. 51.14 divided by 7.67. And Isaac, what do you calculate?
Oh, I was muted. I got 6.67.
6.67 is what we calculate. 6.67. So in each one of these, the ratio is validated when we pop the ratios in to calculate a singular value. So that's how you can double check your values and feel really good about what you've got. Now let's analyze this. How would you, we called this one here earlier a voltage step down transformer and a current step up transformer. We didn't do any current calculations, but the characteristic is if the voltage steps down, the current will step up. Did that happen here? Did the voltage go from a higher level, 75 volts, down to a lower level of 11.25? Yes. Did the current start from a lower current, 7.67, to a higher level, 51.14 milliamps? Did the current step up? So did the numbers validate how we name this transformer? That voltage, if the transformer steps voltage down, it will step up current. And did it in fact step voltage down? And did it also in fact step current up? The answer is yes. There's one more transformer that you're likely to encounter, and that's if I show you this guy. And let's say I have a 4 colon, let's say 17.5. And let's say I have 50 volts on this side. I am looking for everything else. So in this exercise, I am looking for V2. I am looking for I2. I am looking for I1. I am looking for P1. I am looking for P2. 5 items. Can we do this? Sure we can. Yeah, because we know the basic transformer formulas. As long as we remember V1 over V2 equals N1 over N2 equals I2 over I1, and then good old Ohm's law, P IV, so we can confirm the power. Let's see how we go to analyze this. So the first quantity we want, oh, I got to give you a resistor. Let's go ahead and say that this is a 180 ohm resistor R, okay? All right, first task at hand, calculate the V2. How do I set that up? V1 over V2 equals 50 over V2 equals my turns ratio of N1 over N2. And my N1 in this case is a 4 on the top, and my N2 is 17.5 on the bottom, yes? So my V1 over V2 equals N1 over N2. Fill in the numbers, which I have. What do we do now? Cross multiply. And the result of cross multiplying is I have 50 times 17.5, which I'm going to divide by 4, equals my V2. So let's go and calculate that. 50 times 17.5 and divide by 4. Jacqueline, you have a number for me, please?
218.75.
218.75 volts. Wow. We started with how much in the primary class? 50. We ended up with how much in the secondary? 218.75. What happened to this transformer? What did this transformer do? It stepped voltage up or stepped voltage down? It stepped it up. Yeah, this is a voltage step up transformer. Oh, voltage step up transformer. And if it steps voltage up, what do you think it should do with current? Current step which way? If voltage stepped up, Which way did current go? Down. Yeah, let's go ahead down. We're going to validate this in a moment. But that's how you would call out the functionality of this particular transformer, just by looking at the turns ratio also. You have a larger number of turns in the secondary, smaller number of turns in the primary. This better have more voltage on this side, yeah? And in fact, it does. So now let's go ahead and determine our I2. I2 is equal to V2 over R is equal to the 218.75 volts over my 180 ohms. Yusuf, you have a current there for us, pal?
The current for number 2, right?
For secondary, yes.
1.22 amps.
Works out to be 1.22 amps equals my I2. Is everybody okay with that value? I concur. My calculator shows the same. All right. So now we're going to need to find primary current. So for primary current, I'm looking for I1 equals question mark. What approach do we use to find I1? Question goes to Isaac. What do you think?
You would use the formula. So N1 over N2 equals I2 over I1.
I2 over I1. Excellent. We would use the formula. We would use specifically the second 2/3 of the formula and go ahead and fill in the numbers. So I have a 4 over 17.5, and we just newly calculated 1.22 amps over some unknown I1. What do we do here? We cross multiply. And mathematically, this works out to be 17.5 times 1.22 divide by 4 is equal to I1. And so let's go ahead and do that. So Isaac, get ready to get a number for me, 17.5. We're going to multiply by 1.22 and then now divide by 4. And what do you get for I1?
5.34 amps.
5.34 amps is verified. Yes, everybody okay with that? So now let's do some comparisons. Did voltage get stepped up from 50 volts up to 218? Did current get stepped down from 5.34 amps in the primary to a smaller 1.22 amps in the secondary? So we have current step down, yes? All right, so far so good. Everybody okay with this? Okay, so we can put a check mark here. We've done that, put a check mark here, done that, put a check mark here, done that. How about P1? How do I reconcile P1? What's that guy about? Well, you know, we have to have this. Let's go ahead and use Watt's law. So to calculate P1 would be equal to I1 times V1. Does that make sense? If we're looking for power of the primary, we better use power of the current of the primary and the voltage of the primary. And this works out to be my 5.34 amps and multiplied by my V1 of 50 volts. And Yusuf, you're on again.
All right, 267 milliwatts.
So it works out to be, are we in the milliwatt range if we've got 50 whole watts and these are whole amps? Were they not
Sorry, I
whole?
made that milliamps. Sorry.
Yeah, because I think these calculated to be whole amps in this particular exercise. So your number's correct. So 267 watts, yes?
Yes.
Okay, watts. All right. So now we want P2. So P2 is equal to I2 times V2. Jacqueline, we're going to set this up. I2 is going to be 1.22 amps, and my V2 was 218.75 volts. So when I go to clear, multiply 218.75 times 1.22. What do you calculate for power in the secondary?
266.88 watts.
So 266.88 watts. You look at this number and you look at this number. Are they within a few hundredths of a watt from each other? Yeah, within 12 hundredths of a watt from each other. Why are they not exactly the same? Because we were using rounded off answers in many parts of our calculation. So has P1 equal to P2, has that aspect of our transformers been preserved? Transformer formula been preserved? Yes. Okay. All right. Enough for transformers. So how, interestingly, when you encounter there's a question about an automotive part, and the automotive part goes to show, oh, by the way, I meant to say for all of you that these voltages here for transformers are used primarily for our purposes with AC voltages. So this is a 50 volts AC, and this was a 75 volts AC. So it's a 50 volts AC, 75 volts AC, and in all other instances of transformers that we've done were AC, okay? Now, if we take a look at your exercise on the automotive part, you have a 12 volt DC. And 12 volt DC is drawn this way, a few loops here, like so. And then the secondary looks like this.
You shift your paper up, Mr. Co.
There. Like this, okay. Wow. Am I showing, if you had to guess, N1 colon N2, which side has more turns?
N2.
2 has more turns. Oh, this is, by the way, iron core. Okay, N2 has more turns. So what do you think? Is this going to be a voltage step up or voltage step down transformer? Wherever I have more turns, if we go to look back at all of the other illustrations that we've done, if we go to look at all of the other illustrations that we've done, if I have N1 smaller than N2, wherever I have the larger N is going to be where I have the larger voltage. So this side being 4, I had 50 volts. This side being 17.5, I had 218.75. So the larger N numbers where I'm going to have the larger volts. And if I take a look at another drawing here, if you recall, this N for N1 compared to N2, which side had the larger N number? The primary, yes? So if this side has the larger N number, this will have the larger volts. And turns out to be true because our primary was 75 volts, secondary was 11.25. Well, here I've drawn this so that, not telling you what the N1, N2 is, but I'm just simply showing you I've got a heck of a lot more turns here. So guess what? Can we say that N1 is less than N2? Perhaps I do this, double chevron. That means it is much less than N2. So if it's much less than N2, is my voltage going to be stepping up or my voltage going to be stepping down?
The voltage is stepping up.
Yusuf says step up. How many people raise their hands to agree voltage step up? Who disagrees and says voltage step down? Hey, Yusuf, you got everybody on your side. It is a voltage step up. Lots more coils here. Significantly more coils. Now, the way this guy works is there's going to be a switch. And this switch, if I flick this on and off, on and off, on and off, on and off, this will allow the transformer to build up voltage on this side very quickly and also discharge very quickly. So if I change the rate of how fast this thing goes open and close, open and close, open and close, open and close, by making this very, very fast, the voltage will be able to discharge with a very, very large voltage large enough that it will spark is the idea. And if you look at the homework question, what's it physically attached to in your car? It's illustrating something known as a spark plug. And guess what a spark plug does in your car? It creates a what? It creates a spark. And if you have a nice 4-cylinder econo car, so there's 4 cylinders in your econo car, that means you have 4 pistons in here going up and down. So one piston's here, one piston might be up here, another piston's here, and they're all attached to your motor down here, motor crankshaft is what we'll call it. Crankshaft. And what causes these pistons to move up and down inside these cylinders is your spark plug. So there's going to be a spark plug at the top of this guy, top of this guy, top of this guy, top of this guy. And gasoline will come in. For those of you who still drive gasoline-powered cars, gasoline will be injected in here, vaporized, and as the piston comes up like this, it's compressing that gasoline vapor. And so it's right at the top. At the moment it hits the top, this switch is going to flip open and create a spark, a voltage, high voltage onto the spark plug and ignite that spark plug so there will be a spark. And guess what happens when you light up a spark to gasoline? It will do what? It'll do what gasoline does with a spark. It'll explode. And by exploding, it'll force this piston downwards. And as it forces it downwards, it'll help turn your crankshaft. And so as you get a multiplicity of these cylinders going up and constantly compressing gasoline and sparking to come back down, it turns your crankshaft, which turns your engine, which makes your car go. So this is a critical part of your internal combustion engines. It has nothing to do with your electric powered cars, but in your gasoline powered cars, it has everything to do with making it go. So the part is called an alternator, and the job of the alternator is to create a huge voltage step up so that we can control the timing of that spark through something known as, in old cars, it would be a distributor. And in newer cars, it would be called electronic ignition. Okay, and both of these guys control the timing of this switch that creates sparks at a very specific time so that each cylinder fires at a specific time to keep your engine going. Okay, that's all I'm going to say about that, because the pretty much addressed most of the answer to that question without giving you all the giblets. Now, what I would like to also help us out with is this. You'll get a separate worksheet in addition to what I've already assigned, and it'll be a worksheet that'll look like this. I'll just give you a little preview glimpse of it. It'll be a transformer analysis worksheet, and it'll have a transformer illustration, and I will have turns ratio. I'll have the formula specified, and I'll give you some parameters, and I'll say that if N1 is some value, if N2 is some value, if voltage 1 is some value, and the resistor is some value, can you determine all the rest of the things that we determined? And hopefully, yes. Okay, so it'll look a lot like the exercises that we've just finished on these pages. Now, separate of that, something fun and exciting. I have a question for you. How many of you have played with something called Tinkercad? Anybody here play with Tinkercad? Tinker. Jacqueline, have you ever played with Tinkercad? That's a negative. Okay. Wei Ji, have you ever played with Tinkercad? Okay. Isaac?
Nope.
No? Oh, how about Yusuf?
No.
Okay, well, guess what we're going to do? We're going to have some other interesting labs, but this is something that I'd like for you to explore. And so what I'm going to do is I'm going to share a screen here. I'm going to go off of this in a moment. But you go to tinkercad.com, and we're going to go to tinkercad.com in just a moment. Go here and go here and maximize and .com. All right, let me share the screen with you so you can see what we're doing here. Here, and I think it's this screen. All right, tinkercad.com is what I've typed in the address bar. Hit enter, and voila. Woohoo. Can you see my Tinkercad screen? Okay, cool. Because with Tinkercad, what you can do, interestingly, is you can design a number of different things that we can 3D print. Heck, a lot of fun. Oh, it's really easy to do. All you have to do is do a little bit of drawing, and we can do this. Now, let's see. What you do is you hit join now, and then students join a class or create a personal account. So you go ahead and you can create a personal account, because I didn't create one for our class. So hit create personal account, and I'm going to sign up with, let's say, email, and United States, and I'm a January 1 year. I'm going to be a 2015 baby. I'm going to be 4 years old. Sure, why not? Okay, and by username, oh, I love this one. I'm a sample. Oops, hey, wait a minute. Come here. I got to move my cursor in here. Hello, I'm a sample. That's me. All right, my password is going to be username or not, huh? Oh, that contains characters. Username contains characters that are not allowed. It does? Really? Oh, I have a space. Okay, no space. There, it likes that. All right, and my password will be Chabot. Let me try this. Helps if I spell. I'm dyslexic. I can't spell correctly today. Okay, and create an account. I don't have parents' email. Are you serious? I can be an adult.
You are 4 years old.
Yeah, you're too young. That's why you have to be.
Oh, silly me. Okay, I'm gonna have to go back. Yeah, that's right. I am 4 years old. I am such a child. Goofy me. All right, we'll do this as a young adult. Okay, join now. All right, students. No, I'm not joining a class. Yes, images for Tinkercad examples. Ooh, look at this. So yes, you can create by using these objects. You have cylinders, you have spheres, you have rectangles, diamond-shaped things, and in Tinkercad, guess what? You can create hoops, bands. You can change. You can. This one's very interesting. This is a three-dimensional. This is really fun. So 1, 2, 3 rings of different sizes, and each one has an indentation and a bump. So they fit into each other, and they spin and revolve. Isn't that cool as all heck? And that can be manufactured on our 3D printer machine out of a plastic material called PLA or ABS. So this is not hard to design. People start off with some blocks that they can put together. This is a fun design. You can start off with a rectangle and just start carving away different parts of it in order to create your initial. In Tinkercad, you can create block letters. This is so much fun. Wow. And so this is just an example of so many different kinds of things that you can do in Tinkercad. So we'll spend more time on this. But anyway, I'm glad we had our session today. I thank you very much for all being so attentive. We've reached the end of our time together. So I will look forward to seeing you all on Monday. And if any questions come up in the meantime, you know to contact me via Out of the Shadows. All right, 1, 2, and smile, yay. Gotcha. All right, fantastic, guys. Have a lovely weekend and enjoy Tinkercad when you see it.